Hello, good day everyone. My name is Abhay Ratnaparki and I work for IBM Chief Information Office as a lead developer in Austin, Texas, USA. So today's topic of discussion is approximate nearest neighbor search algorithms in information retrieval. So let me go through the outline. So we'll discuss a lexical search, which is a kind of a traditional search engine, how they work, and we'll discuss in the inverted index format. Then we will go to the vector search, see how we can convert documents into the vectors, and the neural information retrieval, how we can use neural networks and where in information retrieval context. And then we'll move to the nearest neighbor search and approximate nearest neighbors. And we'll see some algorithms in the approximate nearest neighbor search context. So let's start with how search works. So the basic search criteria is you have a query and you have to find the matching documents for that query from the list of documents in your corpus. So when you see the search engine architecture, it's basically consists of indexing and ranking. So indexing corpus means getting all the data that you have and making it available into the format which is suitable for retrieval. We call it as an index. Basically the inverted index called as an index. And ranking is a procedure where you have a query, and given a query, you have to find out the number of documents which are relevant and rank them as per their relevancy. So in indexing, when you look into this, you have to get the documents first, and there are multiple approaches to get the documents. One of the famous approach for web search engines is using a web crawler. Like you visit the links recursively, whatever the links in the documents, you try to visit them. Also, you recursively visits those links, like for the new documents that you found. That's how you found the new documents, and you try to grow your corpus by crawling. Um, there are other methods. You can basically search index doesn't care how you are getting the documents, but after having the documents, you have to make some document representation out of those. You have to get for each documents, you have to get some terms out of it and make this index. We'll see index in the detail, how the index structure is, the higher view of the indexing format. But this is a format which is suitable for the retrieval. You can see on the indexing side, you have to do lot of other things, like you have to extract the content. Basically, you may have documents in different formats, maybe images, or you have the thing into the, you might have the OCR images, you want to extract the text out of those. Maybe if you have the HTML pages, in that case, you have to extract the text from HTML. So there are like a lot of different algorithms to do that, how we can extract clean text from HTML, how we can extract text from OCR images. The other things that you have to do is you can do a content enhancement, like if the content is not optimal, you can use different techniques to add some of the fields or connect your documents or enhance your content in a way which is suitable for indexing. Different things involves like deduplication. You might have content coming from different sources, which is essentially the same content. You don't want to index it as a multiple documents. So you use some deduplication techniques or near duplicate removals techniques there. The other things involves like, and which are useful in the ranking, basically doing a link analysis. Like if you are crawling the documents, you already have the connected documents, like your documents are connected to each other, and which basically forms some kind of a graph, and you can analyze that graph to find out the important nodes, do some link analysis to see how much weightage each node has. There are many link analysis algorithms to find out, like in the connected graph structure, find out what's the important nodes are. You can also find out different document features, like based out of different things. If you can use different things like a quality of your content as one of the feature. Maybe you can use the if you have a web documents, like how faster the web documents are being served, maybe that could be your feature. So all these features that you think are useful in your context, you have to gather them at the indexing time. And those features will be useful at the ranking time. So at the ranking, you have a query. You can also do a query expansion. Maybe you can use synonyms and maybe and other things just to expand your query. So make it in such a way that you will get more results. So your recall will be higher. So, and there are different techniques for doing expanding your query. And then you submit that query to your ranker. You get some documents from your index by using your query, and then ranker will rank them, and you will get results. Some of the things on this side is a machine learning based ranking. We call it a learning to rank. So there are many methods how you can rank the documents. How you can relevancy tuning, basically how you can tune different parameters, because the traditional rankers has different parameters which you can tune to get to have the desired ranking. So yeah, that's one of the field. Other field is click models. Basically what happens is when you have the search, the working search systems, the people start interacting with that and like clicking on the search results, copying something, doing all those events. How we can use those events to make search better, and that field is basically a click models, like how you can um, see the user interactions that happening on the search result page and use them to improve your search ranking. And there are like different methods, different click models available for that. Another one is relevancy feedback. Maybe that's again when in the online system you have the search working where people searches and people like some of the search results. How you can further tune your results based out of what a person has liked. So it's a relevancy feedback mechanism. So yeah, a lot of different things involved in the ranking. If you look into the giant web search engines, there are those are like having this plus many other functionalities. There are like open source search engines like Solar. Uh, the Open Search, this is basically a kind of a branch of Elasticsearch, which is okay for which is open sourced branch of Elasticsearch. All this Solar and this Open Search basically under the NIT uses a Lucene library. Lucene is basically an indexing library, which gives you this inverted index kind of a format. But apart from that, there are like a lot of proprietary engines called as the insight engines, because they do more than a search. They do have some kind of NLP techniques embedded. And I have just put like a Gartner's chart to see like who is in the market with the leaders. This is the last year's chart. You can see IBM is a kind of in the leaderboard with the IBM's offering as IBM Watson Discovery, which is a kind of IBM's offering in this space. Yeah, but there are like a lot of other companies offering different things in the insight engine space. So let's move to the inverted index. This is a kind of a basic data structure that's used for the searching. In your corpus, you have the terms. Let's say you selected all the terms in your corpus and call it as a dictionary, all the unique terms in your corpus, like all the documents in your corpus. And you make a kind of this posting list basically on which documents this term is appearing. So if you make this kind of a list, this list will be very helpful at the time of retrieval, because you will be querying by some terms. So you will be readily available the number of the documents on which the term is present. So basically, if you search for, let's say, these multiple terms, then you will just have to see the common documents between the posting lists of the terms that you search for and just return those documents. So returning is not only the thing, we have to rank it. So there are some ranking functions, a very popular ranking functions like a term frequency into inverse document frequency. So if the term frequency tells how many times the terms appears into the document. If the document has a mention of the term multiple times, it means the document is really talking about that particular term. So we have to give some weightage for that. The inverse document frequency, or basically the inverse of document frequency, which tells the document frequency tells how many times, how many documents the term appears. The common terms uh, like A appears in almost all the documents, so its relevance is very less. But very rare terms that appears in very less number of documents. So if somebody search for that, we should actually give more weightage to the documents where these terms are appearing. So that's basically the use of inverse document frequency, and that's if that's more, then the weight of the result should be more. This simple like TF IDF approach is further tuned using some kind of a probabilistic methods. It's called as BM25, and there are some other variants of BM25. It's basically a kind of a ranking function, but it has, yeah, it has some extra features than just TF IDF, but it's basically underneath the TF IDF plus some kind of a probabilistic smoothing over it. And this is a kind of a crux of the open source engines that we have seen, the Solr as well as the Elasticsearch and OpenSearch. Those uses the BM25 as their main ranking function. So this is how the traditional search is, which has inverted index file format, basically works on the text and terms, and you use TF-IDF kind of a things, or with some probabilistic retrieval. So let's move to a vector search. In the traditional search, what we were having is we were having some kind of ranking function to rank the documents. And basically, we consider the documents mostly as a text and converted or index the text documents. Even if it's an image, we will try to get some textual representation of the image and index that document. And basically, we create that inverted index by using the terms that appears for the document. But vector search behaves differently. What we do here is, given a document or any object, there are techniques to create a kind of a vector of that document. The list of floating point numbers, and yeah, we'll see some of those techniques. But basically, that if we can generate them, and if we can generate them in such a way that the similar documents will be generating the vectors which are near to each other, then I think that's a kind of that will be helpful in finding out the documents which are very similar, or the documents which are similar to the queries. But yeah, this is a kind of a generating the vector out of the document, and this is called as embeddings. If we use neural network techniques to generate these vectors, we don't have to. We can use any techniques, or whatever that we want to use to generate the vector out of a document. But nowadays, mostly the neural network based approaches um, are being used because those are like trained on a very large data set. So, and that's why they give a very nice representation of a text into of a text, image, or audio, or any kind of other format into a vector. So yeah, we'll look into yeah, few details of that vector generation or embeddings. But after having these embeddings have been found like very much useful in different tasks. Like, but we are mostly concerned with the search. Uh, but yeah, if we generate these embeddings, we can do a kind of a object recognition in the case of images, or scene detection, or translation, QA, question answering, or semantic search. So yeah, many use cases of the embeddings. In the context of search, if we have, let's say, these many embeddings, and we have these each data point is a vector, given a query, let's say the query is Apple, how can we find out the things or the documents which are near to these things, near to my query? So it's basically all finding out the nearest neighbors, and that's how the problem becomes, as if we can generate these vectors which are, and those in a such a way that the similar vectors are near to each other in the space, the problem goes to like finding the nearest neighbors, and we'll see that. But there are many vector search engines. In the earlier we discussed the traditional search engine, but now we also have some kind of a vector search engines, and some of the vector search capabilities in the existing engine like Solar or Elastic. Though those also have some capabilities, but there are other like full grown vector search engines like Milvus, or Waviate, which has many different algorithm supports. You can go and just use those. If you have those many vectors, you can store them into by using the vector search engine, and then you can use the algorithms just to get those nearest neighbors that we were discussing. We'll see some of the algorithmic aspects of these search engines. So yeah, let's look into how generating those embeddings that we just discussed. Like, to start with, the like word embeddings. Basically, if you can think of it like a word is always characterized by the company it keeps. Basically, it's a similar saying like, you know, you tell me your friends, and I will tell you who you are. It's basically, you can represent, and this is called as a distributed representation. Basically, you can represent a word in the context of other words. In the local representation, the word is just this is called also called as a one hot encoding. Basically, the word is represented as just for itself. Like, if you have n words, you can just have like for the specific word you have the bit set to 1, and for all other words the bit set to 0. So this is one of the way you can encode your word into a vector. But this is one hot encoding. You might need a very large vector, and which is again a very sparse, right? Because there is only at one position there is a 1 and all other zeros. In the distributed representation, you might not need like a very large vector. The vector could be a smaller one, but you can represent your word in the context of multiple words. Like, you can represent banana as a fruit, and plus elongate kind of a, that those properties are true. So you can represent the banana as its properties, and you can set those bits. So this is a distributed representation. How we can, so basically there are techniques. We're not going kind of a details, but those are all neural network based techniques. Started with like word to vec algorithm. Then there are other techniques, and recently like the encoder decoder architecture like the transformer architecture, like a bird, are kind of a popular architecture to generate these embeddings. So basically, transformer neural network architectures are kind of the current state of the art methods to convert to generate these embeddings for different textual or even in the context of images or sound, we can use these transformer models. But there are different types of models. I just listed a few. The models are trained on a very large corpus. There are some models which I haven't listed, which are trained with like billions of parameters, like GPT or T5. And you can, as and when you have a more data, there is a more learning, and you have a big vector, maybe that will, yeah, that has some extra information in it. So you have to choose um, wisely what kind of embedding format that you want to use. But you can see in the vector space, when you have multiple vectors, let's say here, like man and woman may have a similar relationship as a king and queen. So you can do these different operations if you have this vector encoded vector. Uh, okay, so let's go to our topic of converting documents into the vectors. As I discussed, like there are many different neural network based techniques, and we're not going to discuss that because that's not a part of today's discussion. But you can see, like in the context of search, like you have a query and you have the results. Let's say if you have your query is text and your results are text, that's a very common use case. So you need some kind of a model which works for the text. I think if you're starting with this, you can go with like a BERT or sentence transformers. Basically, they transform the sentence or the chunk of the document into a vector. So that's the most useful thing if you are working with the text. If you have, but you have to think based out of like your context. You might have the documents with multiple facets like title, description, keywords. You can and each of it's like a variable length, right? Keywords has just few words, so you can just use the word embeddings for keywords, like a word to vec and other algorithm, other embedding techniques. For title, it may be the sentences, so maybe sentence transformers works best. And for the documents, yeah, those are the larger text, so you have to think like, are you going to generate just one embedding or one vector for the document, or maybe you need to just have, let's say, a multiple vectors for a document. So you have to think on that. Yeah, so you have to think on how you are formulating your problem, how many vectors you are generating per document, like are you going to generate it per paragraph or per document, like just one vector. So, and you have the choices of different embedding techniques. The same thing if your query is text and your output is image. That's one common thing in the image search. When you search the image by using the text, basically when you do that, the web search engine have that option. So basically here again, you have to use some model basically, but think that model, if that model is trained on image and text kind of a pairs, where you have the image and associated text, and if that model is trained on that, you should use that one, because that one will give you the most accurate embeddings. Like here I mentioned the clip models, which is a popular one in this context. The image to image, like if your query is image, your results are image, the convolutional neural network as well as the transformer based models, the neural network models are like useful in this context. I've listed down, like there is this a very detailed block which discuss about different techniques in the context of images. And the same thing like about the acoustics and sounds when you process them, there are like the list of models which are available for you, which you can use to generate these embeddings. Okay, so let's move to the next slide. The next one is the neural information retrieval. So basically, using neural networks in the information retrieval task, that's a neural information retrieval. In the traditional search, we have a query and doc text. Maybe where we can use neural network. The one thing is converting those text into the vector, and then we can also, this is a one point where we can use the neural networks and convert those text into the vectors and then do the operations on the vector. The another point where we can use is at the point of match, like whenever we are matching these queries with the document vectors. So let's look into these diagrams. So these first two actually basically represents um, so here the third one is basically the nearest related to the nearest neighbor search. The other use cases are the different one. Basically, here you have the query text, doc text, uh, and you manually design features, but you use neural networks for the matching. So matching query to the doc, you use some kind of neural network procedures like you use the learning to rank, right, for ranking. In that kind of a context, you can use a neural network based algorithm for ranking. So not for generating the embeddings, but for ranking. In this figure, you can, it's shown like you created a vector, the query and doc vector. So you use some kind of a neural network techniques to generate these vectors, as well as you use a neural network for the matching. So you can use it at both the places. Here you have just used it for generating the embeddings, and you didn't use it at the point of matching, just use a cosine similarity. And this is basically, we are going to see like in the vector search. Basically, you have some vectors for query and doc vectors. You don't use it at the point of the match. You just use the cosine similarity to find out the nearest neighbors. Or in the context of neural IR, you can use it just for expansion of your query. So given the query text, you just expand it, do a query expansion using the embeddings so that your recall will be more. So yeah, so neural information retrieval basically involves all the places where you can use neural networks in the IR task. So let's come back to our nearest neighbor problem. So the problem is finding out the nearest neighbor given the query. Let's look into if we want to find out the top k results, then it becomes like a k nearest neighbor. And here we have to define like a similarity measures, and there are many similarity measures based out of distance and the angle, like inner product, the cosine angle of two vectors. And yeah, there are other similarity measures that those are available. The Euclidean distance between two vectors is the most prominent similarity measures. If you can see, if I have these many vectors, I have to, if I want to find out the nearest neighbors, the one thing I could do is I could look for each and every, get the distance for each and every vector from my current query vector. And that may give me like the that involves like the calculating the distance from the current query point to all other vectors, and based out of that I can just find out the nearest ones, the k nearest neighbors that I want. If you see this, the complexity of this one, this is a navy approach. Naive approach has a complexity if you have the vector of dimension d, and if there are total number of data points, then you have the order of d into n kind of a complexity. So it's a kind of a linear scale, but when you have like millions or billions of data points to search for, this becomes impractical because search systems needs to be online and will be available with very less latency. So, so the thing is with the exact neighbor search or a brute force search, it's virtually impossible to get the results when your data is more in the with given accuracy. There are some with this exact neighbor search. There are some algorithms which improve it, which tries to improve it using, let's say, space partitioning, and I mentioned it here. But in real world, when your dimensions are more, basically those algorithms won't work, or those won't work better than the brute force one. So we are not going to discuss that, but instead, what if we can trade off accuracy for a latency? And if we can try to do some kind of a approximate algorithms to find out these documents. So can we do some approximation and make our algorithms very faster? Uh, so yeah, we'll be discussing that. And the first one in this context is inverted file index. This is a very simple approach. If you look, we have this search space. What we do is we have to make these various regions by using some kind of, we may use like a clustering techniques like k-means to get these different regions, or these are the centroids for each one of these regions. So it's basically we partition the input data into multiple segments, and whenever the query comes, we can just search on that segment. We don't need to we don't need to search on other segments. So this is an approximate algorithm because sometimes if your queries lies on the boundary, the nearest neighbors might be on just the adjacent cells, but you're not reporting that. You're just searching the cell that your centroid belongs to or your current query vector belongs to. So this is a inverted file index. Basically, it has some to get like some more accurate results. You can also set this n probe, means how many adjacent cells that you are searching for. Maybe you can set n probe to some greater number to search some adjacent cells to the given query vector. Yeah, that's a kind of some tuning you can do here. The simplest algorithm and traditionally generally used in combined with some other algorithms. So let's look into the tree-based algorithm for approximate nearest neighbor search. Uh, Again, like this is called as ANOI, the approximate nearest neighbor OER. I don't know why they put it like this name, but this is a really simple and intuitive algorithm. So let's look into this. We have these data points into, let's say, 2D plane. What we do is we select any two random data points. Let's say we selected 5 and 6. Then we have to select the, in this case, like 2 dimension, it's a line, but in actual n dimension space, it's a hyperplane, which is separating these two vectors. We have to find that hyperplane separating these two vectors. So if we connect them and get the perpendicular line, it's a kind of a hyperplane separating these two vectors equidistantly. So we draw this black line and separate the input space into the regions. Again, we have to do the same thing recursively, like find out any two different points. Let's say we find out like 3 and 2, and then we use these another line to separate the regions. And maybe we might have some stopping criteria here. If we have the region has 4 or less data points, we are going to stop. So here we stopped it. So we named our region as R1 and R2. In the same case, we partitioned it by choosing, let's say, some random points. We chose 8 and 9, and then this is a line separating these points. And again, we chose, let's say, 10 and 13 and put this R4 and R5 region. So the thing is, as we know what points belongs to which regions, we can, for the nearest neighbor, given a query, we just need to search for this region. Let's say if my query lies over here, I just need to search for R3 region, and maybe I can report the nearest neighbors in these regions only. So to get to the R3 region, we maintain like this kind of a tree kind of a structure. And we again go in the same way to find out like where exactly the query lies. So we have to traverse the tree and go to the particular region to see like if my query is here, my query lies here, I will have to see if it lies above or below this line. So I can check this node of the tree. It lies above, then I have to go and check to the next line separating the hyperplane, which is 8 and 9. So I have to see if my query lies, where exactly my query lies, below or above this line. So in this case, if it's below, then I know it's R3 and I am aware of what are the points into the R3 region. So I just need to calculate the distances for these many points. Again, it's approximate because if my nearest neighbor could lie just near the boundary, could be there, could be other nearest neighbors. And it's possible that we are, and that's why like we are trading off some of the accuracy for the latency of the performance reason. So this is a tree-based algorithm. The another nearest neighbor algorithm is graph-based, and basically this is too much prominent because it's in the real world, it's the fastest algorithm, and it has a concept of small world graph. Let's say if you have this graph, let's consider you have the graph and you have a query vector. And you start from some of the node from the graph to find out the nearest neighbor for this query vector. You have to, for the entry point, you will see what are the connected nodes for your entry point, and then find out of them which one is the nearest to your query vector. Let's say this one is nearest to your query vector. Then again, you will do the same thing. You will find out the connected nodes of this one, find out which next node is nearest, then this one is nearest, and that's how you traverse, and you will find the connected the node which is near to the query vector. The idea is this is called as a small world graph uh, because each node has some small number of connections. Basically, if you have a fully connected graph, then your computations will increase, right? You have to select for each node all the connected nodes. So the connectivity should be small, like each node should have the small number of connections. And the another property that small word graph has is the average hop count between randomly selected nodes should be low. And because you are traversing the graph, that's why like average hop count that you want to traverse to get the nearest neighbor should be less, right? Yeah, the small word graph is a kind of a property of the graph being not only used in this algorithm, but yeah, it's also used in other fields where like the mobile ad hoc networks and other places where this really makes sense to having these kind of where the routing and the flow is required to find out to reach from one node to another node with the less number of hops, and the graph, you should be able to reach it. The graph should be connected, but it shouldn't be like connected in such a way that reaching from one node to other is really expensive. So that's why it's called as a like a navigable small word graph. It works on that. The other concept that this hierarchical navigable small world algorithm basically gives us this layered graphs. So as and when you have for your data points, you create a graph, which is a small word graph. As and when you get new nodes, you just insert in a way that there are some small number of connections uh, there for every node. But what happens is, again, if as I said, like there is a trade-off, you still have to traverse. Can we do that faster? Um, by taking the intuition from the skip list data structure in the context of linked list, where if you want to search faster, you can just skip some nodes and just have some extra pointers to the next nodes. In the same way, we can have some extra pointers into the graph with different layers. Like with this layer, we might have layer 0 is, let's say, densely connected. Layer 1 is sparsely connected than the layer 0. And maybe layer 0 is only having the few nodes, and we can have this layered structure maybe for n layers. But the layer above is just maintaining some long distance relationships, and layer below might have some more connected relationships. So what we can do is we'll start with some entry point into the above layer, let's say the top layer. We'll see the connected node. Maybe this is the here there is only like one node which is connected to this one. So we will see this. If this is near to our query vector, we will just uh, we'll go to the next layer, maybe uh, the layer below, and then see the traverse and see what's the nearest node. And maybe we can again go to the lowest layer, and then we will get the maybe the nearest neighbors. So it's basically the traversing time is faster because you are skipping many of the nodes, because you are maintaining some long distance relationships into the above layers. So this is and that's why like this layered architecture is very much helpful, because it helps you reducing your latency. The cost here is you have to store more number of nodes, more graphs into the more layers. So your memory and footprint will be more, but yeah, you will gain at the time of retrieval by reducing the latency. So yeah, this is the another techniques basically in the approximate nearest neighbors include the vector encoding called as a, and one of the important vector encoding technique is locality sensitive hashing, LSH. The concept over here is you want to in general the hash, like in the traditional hash table, you want to avoid collision. Like you try to put input data in such a way that you try to avoid collision. But in locality sensitive hashing, the idea is the similar documents, and here the similar means the documents which are near to each other, we try to put them into the one same bucket. Like the documents which are near are put into the same bucket, and that's how we choose the hash functions. Basically not one but multiple hash functions, and that's what this LSH algorithm is a kind of a standard algorithm in information retrieval used in many different places. Basically, we use it for near duplicate removals, also finding a very similar document, not exactly but near similar documents. That's where the LSH being used. But here we use hash functions to hash these documents, the documents which are near into the same bucket. So at the time of searching, we just need to see where the query hash is, and just need to search that particular bucket, which reduces our search space, and that's how like increases our latency of the searching. The another important like vector encoding technique is called as a product quantization. There is some mathematical aspects about this technique, how we can, but the idea behind the product quantization is, if we have a vector of n bits, how we can reduce it into some kind of a code which is a very small as compared to the original vector. So if you can see here, the original vector is 128 bit vector, 128 floating points. So you can see it's a 512 bytes vector. Can we reduce this 512 bytes vector into a very small representation? In this case, let's say 8 bytes. And there are techniques to do this. So let's look into those. If we do this, then our memory footprint for storing those vectors will be very less. So basically the idea here is to get the product quantization code out of original vector, and this PQ code should be very small in size as compared to the original vector. So to do that, what we do, let's say we have the number of data points or all the vectors. And this is like we have, let's say in our corpus, we have 1000 vectors. What we do is we have to, let's say, the one vector is divided into multiple vectors. Here, let's say a 128-bit vectors is divided into 16-bit vectors, like 8 such vectors. And we get this space, like for each and every vector, we have these first 16 bits here. So we put like, we apply some kind of clustering technique here on this part to get centroids. Let's and we can define like how many centroids that we want. Let's say here we want, let's say 256 centroids. So we try to generate like these maybe we can use like a k-means kind of a clustering algorithms to get these centroids. Like we make like 256 clusters out of these data points and get 256 centroids. In the same way, like for the other parts, we get more centroids. And this will generate a code book for us. So basically, given all set of vectors, we will have a code book which has a 256 centroids in total. So this code book is being used further at the time of retrieval. But here you can see, given an original vector, you will just try to get, let's say if you have a new vector coming in, you will try to see, you will divide it into the 16 bits, multiple vectors, and you will try to see which centroid, like out of this 256, which centroid this particular part matches to. And you will just use, and because there are 256 centroids, you just need 8 bits to represent that. And that's how you get, let's say, your original vector is represented into a set of into the centroids of some smaller vectors. And that's how you get like a too much reduction into your original vector and you will get this kind of a PQ codes. And let's look into how those PQ codes are being used for searching. So you have the vectors, and whenever your query comes, you use that code book that we explained before. It's basically the list of centroids, basically that you generate from all the data points. So you have this code book. You use that code book with your query vector to find out this distance table. Basically, that distance table you create for a query by using the code book that you have. And this distance table, you have to, you don't need to use the original vector, but you have the PQ codes already generated for all the database vectors. And you can use those PQ codes with this distance vector and do some kind of a partial distance matching. This matching is very faster because the PQ codes are smaller and you have a small distance table. So you have to match here. You have to match like your query to each one of the PQ codes. But yeah, and again you have to sort the results to get the nearest neighbors. But still, this is a very much faster technique. I think this is the fastest technique for finding the approximate nearest neighbors. And basically here you have a lot of parallel computations you can do. So you can also use like a GPU kind of a machines to make it the faster and do this computation in parallel. Yeah, so this I request you to look into these blocks. I think these blocks really explains all these techniques into great details. But what are the things is there is always trade-off between latency and accuracy. So it depends on your use case, your data, and if you can provide like extra space. Do you have a GPU? Depends on all these factors. The kind of a technique that you want to choose for ANN algorithm changes. I've listed down like some of the guidelines that are there in this Facebook AI similarity search PS library has mentioned. But yeah, those are just the guidelines, but based out of like your data and everything, we have to think of what's the best thing or best algorithm to choose for the ANN. Okay, so that's it for the talk, and this is my LinkedIn. If you have any questions, feel free to just ask me over the LinkedIn. Thank you.